So welcome to the next unit in IB Chemistry, Topic 5, Energetics and Thermochemistry, one of my favourite topics of all the mathematics. Okay, so basically this unit's going to be broken down into 5 parts. Okay, the SL stuff will be around measuring energy changes, which we will look at today. Then we're going to look at calculations around Hess's law, then bond enthalpy calculations, and then for the HL stuff, energy cycles, again, probably related to Hess's law, and the concepts of entropy and spontaneity of reactions. So in terms of what you need to know that heat is a form of energy, that temperature is a measure of the average kinetic energy of particles, total energy is conserved in chemical reactions, and that chemical reactions involve the transfer of heat between the system, the chemical system, and the surroundings. And this idea is the idea of endothermic and exothermic reactions. The enthalpy change for a chemical reaction is indicated by kilojoules per mole, and you can basically express them under a standard condition, which gives that little naught sign. And you should also be able to calculate the heat change for a temperature change using the equation given, and we'll also look at a calorimetry experiment for the enthalpy of reaction, and the results will be evaluated. The first thing we're going to look at is the difference between temperature and heat. Okay, so temperature is the average kinetic energy of a group of molecules in a particular compound or particular reaction. Okay, so if we have a plot of the kinetic energy, the energy that the particles are moving at, and the actual number of particles, okay, it will actually fit kind of on a normal distribution curve, okay, and the average energy, kinetic energy, is going to be kind of where most of the molecules sit. So even if you have basically boiled water, okay, most of them have an average kinetic energy in the middle, but some have very low kinetic energy, and actually some will have very high kinetic energy. Okay, so it's going to be an average of all the molecules within that cup of boiled water. So heat is the amount of energy exchanged due to a temperature difference between two substances. Okay, so that's the difference between heat and temperature. Heat is actually the transfer of energy and the amount of energy being transferred. There's more a physics concept in that. And last year you would have looked at the idea of enthalpy, and enthalpy, which is given the symbol capital H, is the amount of energy or the heat content of a substance. It's basically the energy that is stored in the chemical bonds. So it includes both the kinetic energy, so the energy of the particles moving around, but also the chemical potential energy, which we looked at briefly in the last unit, which is actually locked in those bonds. And it's not actually measured directly, so you can't know, say, the enthalpy of carbon dioxide when it has been combusted from the enthalpy of the carbon and the oxygen, but the difference between the carbon dioxide energy that's been produced and the energy of the reactant carbon and oxygen can be measured. And it's measured, of course, in the units of joule because it's a measure of energy. And the standard enthalpy of reaction, okay, that little naught there, is the difference between the enthalpy of a product and the enthalpy of the reactants at the temperature of 298 Kelvin and a pressure of 1 times 10 to the 5 pascals. So looking again further into this concept of enthalpy, so the change in enthalpy, delta H, okay, so that little delta, of course, from last year is equal to change, is the enthalpy of the products minus the enthalpy of the reactants. It's basically the heat energy per mole. So there's the equation there, okay, which you would have been familiar with in IGCSE. Delta H equals the enthalpy of the products minus the enthalpy of the reactants. For exothermic reactions, the temperature of the surroundings increases, okay, so energy is being released to the surroundings, so that means that the delta H is negative. That basically states that energy is being given from the system to the surroundings. Whereas for endothermic reactions, the temperature of surroundings decreases relative to the system, and delta H is positive because energy is now being absorbed from surroundings into the system. The higher the enthalpy, the less stable the substance. That's something probably you didn't learn last year. Last year you would have also looked at enthalpy level diagrams, just kind of revision, and we looked at the enthalpy level diagrams for endothermic and exothermic reactions, so you can see the clear difference. So in an endothermic reaction, there is a lot of energy required to break the bonds of the reactant, and this energy of course comes from the surroundings, and the amount of energy that's released when the bonds are formed is a lot less than the energy that is required to break them. So the net energy change is of course positive because you've got energy having to be used to break the bonds of the reactants. Whereas for the exothermic reaction, the energy change required to break the bonds of reactants is a lot smaller compared to the energy that is released when the bonds actually form to form the products, which means that their net energy change is negative. More energy is released than is required to be absorbed to break the bonds of the reactants initially. And that's what we see by the following diagrams. You also notice that little hump on the top, of course, that is the activation energy. Okay, so a large activation energy, so for example the formation of nitric oxide from nitrogen and oxygen, means a lot of energy is required in order for that reaction to occur. Okay, it requires basically higher reaction temperatures, unless we move into things like catalysts. Whereas the formation of phosphorus pentaoxide from phosphorus and burning in oxygen has a lower activation energy. Okay, which means of course that it is a exothermic reaction, highly exothermic, as opposed to the nitric oxide formation, which of course is endothermic, because there is more energy locked up in the nitric oxide than there is compared to the locked up in the reactants. Whereas for the formation of phosphorus pentaoxide, it's highly exothermic. There's more energy locked up in potential energy locked up in the bonds of the reactants, phosphorus and oxygen, compared to the product, phosphorus pentaoxide. So energy is actually released. So the energy is measured. This energy that's been released is measured in temperature, okay, or absorbed for that matter, if it's an endothermic reaction, and we can only calculate the energy change. Okay, we can't calculate the amount of energy that's actually inside the reactants or products. We can only determine the difference between the energy in the reactants and products. Yeah, so you can't basically calculate the energy stored in the resulting products or reactants. Only the difference between the two. And there we go. That's just kind of reinforcing it. Exothermic reactions, the energy released means that the delta H naught is negative, whereas for endothermic reactions, the energy absorbed from the surroundings means that delta H naught is positive. The enthalpy is positive. So in terms of exothermic reactions, examples include of course combustion reactions, exothermic energy is released, and neutralization reactions with acids and bases, again energy is released. So in an exothermic reaction, the products have less stored energy compared to the reactants. They are more stable compared to the reactants, and they have stronger bonds compared to the reactants. In terms of, so that's what we have for exothermic reactions. So in terms of heat energy change, the equation that we've used from last year, Q equals mc delta T, where of course M is the mass in grams, C is the specific heat capacity, usually for water, and delta T is the change in temperature in Kelvin, where Q is the heat energy change, and delta H, heat energy change per mole. Okay, so delta H equals basically the heat energy change per mole. So the techniques that we use to measure these temperature changes is known as calorimetry. okay, to use these enthalpy changes. And the heat absorbed equals Q M times C times delta T, where C is usually water. Okay, we usually water the temperature change, so basically you have a reaction that will actually boil water. And of course the mass of water will be 1 centimeter cubed, because that's the density of water, 1 centimeter cubed or 1 gram per centimeter cubed. So the first one we would use is the styrofoam calorimeter, maybe for neutralization reactions, which has a thermometer, of course, to read the temperature change, a glass stirrer, so you can stir the reaction, a cork stopper to stop, I guess, excess heat loss, and 2 styrofoam cups nested together containing reactants in the solution, again to stop this heat loss, to get a reasonably accurate result, because you don't want to lose the heat to the surroundings as opposed to the thermometer, which is measuring the temperature change. It's quite good for solution chemistry, say acid-base chemistry, and working out enthalpy of neutralizations. And the other one is a bomb calorimeter, this time using a motorized stirrer. In this one here, you actually ignite the material inside the calorimeter. Okay, that's what the electric leads are for. Again, a thermometer to read the temperature change. An insulated container, because again, we don't want heat energy to be lost to the surroundings. We're going to go straight into the thermometer. An oxygen inlet, because we're doing combustion, so you need oxygen to come in. A bomb, which is essentially the reaction chamber, and a fine wire in contact with the sample to allow the reaction to be detected. And of course, you've also got water, notice, around the bomb, because that's what the temperature change we're measuring. We're measuring the temperature change in the water. And we have the cup holding the sample. So basically, we ignite the reaction inside the bomb calorimeter, and we can then measure the temperature change. So of course, there's lots of assumptions and errors associated with calorimetry. Okay, so again, there's no heat lost or gain from the surroundings. That's the reason why we have this insulation of the styrofoam and having insulated bomb calorimeters. There are significant errors, of course, though. Essentially, the evolution of gas will cause probably a lower value for the change in temperature. And those reactions involving combustion, where hot gas is used to heat a liquid in a calorimeter, again, this could cause problems in getting an accurate measure of temperature. So as the heat rises and the change in temperature under these conditions are reported to be less than literature stipulates because of these sources of error. But the thermometers themselves usually have a precision around uncertainty of about plus or minus 0.1 degrees Celsius. So they're quite precise and accurate, at least as a tool. So how do you measure temperature changes graphically? Well, temperature is constantly changing to return to room temperature, so lines are basically extrapolated from a graph to calculate the change in temperature. Okay, so the reaction is over and the mixing is cooling here. So here's the reaction between zinc being added to copper 2 sulfate. So you've got this displacement reaction, the more reactive zinc displacing the less reactive copper 2 plus ion. Okay, so over time you can see basically initially the temperature is around 20 degrees. You add them together, then you have this big jump in temperature change due to the nature of the exothermic reaction. Okay, so you get a jump up to here, and the maximum jump is the delta T, which we'll put into our equation. And essentially, we can then extrapolate back onto the y-axis to get the actual value of delta T at time 0. Just to finish off, we'll just do some worked examples and problems to see how this would look like in an exam situation, what kind of questions you could be asked. Because the first one is problem 1. 1200 kilojoules of heat is evolved when 2 moles of magnesium react completely with 1 mole of oxygen. How much energy is released if 0.6 grams of magnesium is burnt? Okay, so we've got some numbers. We've got 1,200 kilojoules of heat being released or evolved. So we're looking at an exothermic reaction probably. Then we've got 2 moles of magnesium and 1 mole of oxygen. and the energy released if 0.06 grams of magnesium is burnt. So what equation shall we use? Well, the first thing is we'll just pause the video now for you guys, just see if you can actually work it out for yourself, and then we'll go through the answer. Right, so the equation for the reaction is 2 magnesium going to plus oxygen, combusting, giving it like that bright flame we're probably familiar with, and that gives your 2 magnesium oxide, the white powder. And we're told that the enthalpy of combustion is going to be 1200 kilojoules per mole, okay, divided by 2. Now why 2? Why 2? Well, you've got 2 moles of magnesium. We're told already we've got 2 moles of magnesium. So that means the delta H of combustion, the change in enthalpy of combustion for magnesium, is going to be minus 600 kilojoules per mole. So the number of moles of magnesium is going to be, again, going back to stoichiometry, mass over molar mass, which is going to be 0.6 divided by 23.3 grams per mole, which of course is the molar mass of magnesium. So you end up with 0.0247 moles of magnesium. And then we can use our equation that we just learned. Delta H equals the heat change divided by number of moles. Plug in the numbers, and you basically get 14.8 kilojoules, which is evolved. Okay, so that's the amount of energy that's evolved from the reaction. So the next question asks, what happens when you add 20 centimeters cubed of 2 molar sodium hydroxide to a 30 centimeters HCl solution of the same concentration, and you get a temperature increase of 12 degrees Celsius. And you're asked to determine the heat that is released, because of course it's going to be released because it's a neutralization reaction. So pause the video now and see if you can work this out by yourself. Right, so the first thing is the total volume will be 50 centimeters cubed. Reason being, 20 centimeters cubed plus 30 centimeters cubed equals 50 centimeters cubed. We already know as well that the density of water is 1 gram per centimeters cubed, so the mass of the aqueous solution should be 50 grams. So the amount of heat required to heat the water is going to be Q equals MC delta T. We plug in the numbers, so mystery value is Q equals 50. The mass times the 4.18, which is the C, the specific heat capacity for water, times the change in temperature, 12 degrees from the question. And we get a value of 2.51 kilojoules. Okay, so far so good. However, we also have to do it from the perspective of number of moles, because remember, the heat release is going to be in kilojoules per mole. So 2.51 kilojoules is the amount of heat released in the reaction of hydrochloric acid reacting with sodium hydroxide to give salt and water. So the sodium hydroxide is therefore the limiting reagent. The number of moles of sodium hydroxide is going to be C times V from stoichiometry. We plug the numbers in, we get 0.04 moles. So that way we can actually determine the enthalpy per mole, okay, rather than just the enthalpy. So delta H, sodium hydroxide, is going to be Q divided by N, or 2.51 divided by 0.04, or 62.7 kilojoules per mole, which is the amount of energy that is going to be released. Okay, it's an exothermic reaction, so delta H, of course, you need to put on the negative because it's an exothermic reaction. Negative 62.7 kilojoules per mole. The final example is 300 centimeters cubed. Okay, so just kind of circle these things. 300 centimeters cubed of 0.2 molar aqueous potassium hydroxide neutralizes 150 centimeters cubed of 0.2 molar sulfuric acid. We go for an average initial temperature of 22.3 degrees Celsius, to a maximum of 29.2. Oh, delta T, question mark. Calculate the molar heat of enthalpy of neutralization of potassium hydroxide and the molar heat of enthalpy of the following reaction, and it's even given to you as a balanced equation. So pause the video now and see if you can find an answer. Right, so this is what you should have got. So Q equals MC delta T is the equation you should have chosen. You basically bang in the numbers, and again we're looking at the mass due to the density of water being 1 gram per centimeters cubed as being 300 plus 150 from the two solutions being added, times 4.19, which is given in your data book, multiplied by the change in temperature, which we get from the question. So you should get, start off with roughly 13,000 joules of energy. Now, of course, the number of moles of KOH equals C times V, which will be 0.06 moles. Number of moles of sulfuric acid will be 0.03 moles from our stoichiometry equations. So for the molar enthalpy of combustion of neutralization of KOH, delta H equals Q divided by N, which will be your negative 13.1 kilojoules from your first part of the equation here, divided by 0.06 moles, which you just calculated, which will be negative 217 kilojoules per mole of KOH. So for the molar enthalpy of the reaction, you need to watch for the stoichiometric ratios. There are 2 moles of KOH, okay, 2 moles of KOH for every 1 mole of sulfuric acid. So that means you have to divide that number by 2. Okay, so delta H is going to be Q divided by N, which is going to be negative 13.1 divided by 0.03, which gives you the final answer of minus, which is good because it's a negative, 109 kilojoules per mole. Okay, because we're looking at it per mole. And that is pretty much measuring energy changes.